Hello, today we're going to start a series of videos on the unification of physics. What do we mean by that? This is a snapshot of what we know about our universe today. We have two theories, general relativity, which gives us our theory of gravity, and it counts for the large-scale physics, anything from a few inches out to astronomical distances. On the other side is a standard model of particle physics, and it tells us about the physics on small scales, the atomic and subatomic realm. And those are the two theories that tell us most of what we know about our physical world. But there's a problem. The mathematics that underlie the general theory of relativity, the logic that is used to support it, is entirely different than the logic used to support the standard model. We don't exactly know what the underlying logic is that supports the standard model, but what we do know is that whatever it is, it's different than the logical foundations for the theory of relativity. What we would like to do is combine general relativity with a standard model and produce a quantum theory of gravity. This is the hypothetical theory that doesn't exist yet, but we would like to have our universe described by one theory instead of two conflicting theories, and that's what we call the unification of physics. And if you'd like more detail on this subject, you can go to my website, www.roadtoatoe.net, and there you'll find 4 books that go into more detail. But this series of lectures will give you an overview of what you'll find on the website. Now, I should point out that the general theory of relativity is a completely predictive theory. What that means is it requires no supplementations to make its predictions. We don't have to put in artificial inputs or anything like that. It's a wholly contained, completely predictive theory. That's not the case with the standard model. The standard model is not a completely predictive theory. It has to be supplemented with additional mechanisms before it can make predictions. General relativity has basically one interpretation, the space-time interpretation. Most physicists agree that gravity is the warping of space and time in the presence of matter and energy. You won't find other interpretations of general relativity, except maybe speculative ones. On the other hand, the standard model has lots of interpretations, maybe 10 or 12 or so that people put forward at various times. Physicists really haven't agreed on which interpretation the standard model should have. This is a debate that goes on in the physics community, and if you hear physicists talk about the measurement problem in quantum mechanics, that's generally what they're talking about. General relativity is a wholly self-contained model, but the standard model isn't. However, it does have a theoretical part. It's called QFT, quantum field theory, but it has to be supplemented by mechanisms that aren't part of the theory, and one of those is about 19 or so adjustable constants that have to be set so that the model can make its predictions. These constants have to do with the masses of the particles and other things. Not important that we know all that stuff yet, but that's essentially what's in this box, is adjustable constants. And depending on what energy levels, the constants need to be adjusted before the model is run. And if you hear physicists refer to fine-tuning, or if you hear them using that term, that's what they're talking about. This is an undesirable feature of the standard model because we would like to know why the constants have the values they do, and we just don't know that. The next supplementation that the model needs is something called the Higgs mechanism. I'll just write Higgs here. All the particles in quantum field theory are massless particles. Some of the particles in the standard model have a mass, and the Higgs mechanism describes how particles gain mass, so that has to be added to the model. And finally, there's one more piece. I'll just write an R in this box, and that stands for renormalization. Renormalization, and what is that? If you've heard physicists talk about perturbation or perturbation theory, that's what it relates to. What it involves is, suppose I have a very complex function. It turns out that I could approximate that function with a series of simpler functions. I'll write f1x, and for these functions, f2x, on down, that are a lot easier to work with. In most cases, the series of functions has an infinite number of terms. And that doesn't necessarily mean that it's a bad thing. For example, I can add up something like this, where n goes from 1 to infinity. And if I do that, that happens to sum to 1. And if the answer makes physical sense, then I can incorporate it into my theory. Unfortunately, that doesn't always happen. If a series sums to a finite number, mathematicians and physicists say that the series converges. But not all series converge. I can sum here, and again goes from 1 to infinity, and that's going to be equal to 1 plus 1, plus 1 plus 1, and be equal to infinity. Infinity isn't a good answer if you're trying to say something about the physical world. So renormalization involves ways of getting rid of the infinities, and there's a couple of ways you might do that. For example, sometimes in these complicated calculations, you have a finite part, I'll just call it f, plus an infinite part. And if the infinite part doesn't really have a physical meaning, it's just a mathematical anomaly, I can throw away the infinite part and just take the finite part and put it into my theory. That doesn't happen very often, but sometimes that's what happens. The other thing I might do is cut off the sum after a finite number of terms, which would give me a finite answer, and argue that the terms past the cutoff, I'll call this the cut off, terms past the cutoff don't contribute much to the sum, and so I get a finite answer. If that makes physical sense, I can put that into the theory. And lastly, I can maybe change the parameters of the theory. For example, if I substitute 1/2, then I would get 1/2 plus 1/4 if n equals 2 plus 1/8, and that would sum to 1. If it makes physical sense to do that, then I could put that in the theory. Again, renormalization is just the ability to get rid of any infinities when they arise in the calculations, and they arise a lot, so that's a very common feature of the standard model. It turns out that the standard model is renormalizable. It's a completely renormalizable theory. I can always find ways of getting rid of the infinities when they arise in calculations. However, we might think of applying general relativity to small-scale physics and see if we could use renormalization to get sensible answers. And the answer to that question is we can't. General relativity is not a renormalizable theory. No matter what tricks we use to try to get rid of the infinities, they don't go away. So we can't apply general relativity to small-scale physics. It just doesn't work. And so that's one of the reasons it's difficult to unite general relativity to the standard model, is because one is completely renormalizable and the other one isn't. The purpose of these series of videos is to show you how we got to this point. And so let's get started. Well, the story begins a long time ago, back in Greek civilization. Aristotle was really the one who talked about the nature of the physical world more than most philosophers did back then. His belief was that nature was made of 4 elements: earth, wind, fire, and water. Now, he had a couple of beliefs that were wrong. For one thing, he thought that gravitational mass was not equal to inertial mass. What did we mean by that? Well, I'll explain it in a minute. And he also thought that moving at a constant velocity was not the same thing as being stationary. And those were two beliefs that he held that turned out not to be the case. So what does it mean to say that gravitational mass does not equal inertial mass? Aristotle believed, as if you got on a tower here and you threw off a heavy object and a light one, that they would fall at different rates, that they would hit the ground at different times. A few centuries later, Galileo showed that if you threw 2 objects off the Eiffel Tower, that the smaller one and the larger one would hit the ground at the same time. Suppose that these 2 bodies were just sitting in outer space with no gravitational field around, and they were just floating there. That's called inertial mass. And suppose we accelerated the tower up at a constant acceleration, g. If gravitational mass is equal to inertial mass, then this would be the same thing as if this tower was at rest in a gravitational field and these 2 balls were accelerating downward at an acceleration, g. Those two physical environments are exactly the same, and that's what physicists mean when they say gravitational mass is equal to inertial mass. And that's what Galileo showed, and that didn't square with what Aristotle thought. Aristotle believed that a constant velocity was a different state than at rest, but Galileo said that wasn't true. I'll read you this, you probably can't see it. The laws of physics are the same in all inertial frames of reference. That became known as Galilean relativity. Being stationary and being at rest were the same physical environment. Galilean relativity became very important in the future of physics. It had to be modified somewhat later on, but we still believe that this is true, that gravitational mass is equal to inertial mass. Now, Aristotle was so revered that the Roman Catholic Church adopted him as the official philosopher of the church, even years after he was gone. And so when Galileo published his beliefs, which contradicted Aristotle's views, Galileo was called up and forced to renounce his beliefs in front of the church's Inquisition. But eventually, Galileo's ideas proved to be correct. The next big leap in our understanding of the physical world came at the hands of Isaac Newton. This was a huge leap forward. Newton published two monumental works. Here's one of them. It's called The Motion of Bodies. You can see it here, and it's a fairly hefty volume. You know, it's thick. Let's see how many pages, 400 pages, and that's not all. He published The System of the World, and this one was 600. Oh, it continues. So the whole two volumes were 600 pages. I guess the starts where the other one left off. So that's a pretty hefty contribution, to say the least. And what was really remarkable about Newton's contribution was that ultimately it was based on these three notions and these three laws. Everything you saw in those volumes was based on these six things. Space was synonymous with distance. We have a distance r between two things. Time was used because if you wanted to describe motion in space, you had to have time. You did that in time. And then matter was just something that had weight. Newton's first law was just Galilean relativity, and that said that all bodies would move at a constant velocity or stay at rest unless a force acted on them. And that was essentially the same as Galileo's insight. The second law was force equals mass times acceleration. Mass was the matter part, and acceleration was motion, so that involved space and time. That was movement through time. And the third law is every action has an equal and opposite reaction. And that just says is that if we apply a force to a body, that force acts on the body until we remove it or apply an additional force. Now, Newton's great insight was that apples fell from trees for the same reason that planets orbit the sun. So he provided us with a theory of gravity. Newton gave us this formula that said that two masses attract each other proportionally to the square of the distance between them. Now, one thing, Newton's law is an action at a distance formulation. These two masses, this would be the mass 1 and the mass 2, separated by a distance r. This was the space part. The masses were the matter part. What about the time part? How long did it take for this mass to know that this mass was exerting a force on it? That turned out to be t is equal to 0. And that was a little bit of a controversy. Even Newton didn't like that part of his theory. How did the two masses know instantaneously that the other mass was exerting a force on it, no matter how far away they were from one another? That will turn out to be something that needed to be changed in Newton's theory. Now, the next big leap in our understanding of the universe came from Maxwell. He produced a theory of electromagnetism. And before Maxwell, the theory of electricity was described by Coulomb's law. And it looked just like Newton's law. It was an action at a distance formulation, except the masses were replaced by charges separated by a distance. The only difference was that charges could be plus or minus, and if the charges were like, Coulomb's law predicted like charges repulsed, and if the charges were different, there was an attractive force. Now, before Maxwell came along and wrote his theory, optics, which is the theory of light, electricity and magnetism were all covered by different theories, and no one understood these were manifestations of the same thing. In fact, there was a debate about whether or not light was a particle or a wave. And Newton wrote another fat book on light. It's called The Optics, and it's about 400 pages long. So it's a hefty contribution. He shined light through a prism, and it split white light up into different bands. And he thought, well, since the bands came out in straight lines, that light had to be particle-like because waves tended not to travel in straight lines. But in about 1803, Thomas Young shined light through three little slits and noticed these alternate light and dark bands. That was typical of wave behavior, not particle behavior. The way he determined that is if you have two waves, like this, and a crest lines up with another crest, you get these light bands, and if a trough lines up with a trough, you get these darker bands in there. But if a crest lines up with a trough like that, they cancel out, you see these dark bands. And so he concluded from that light was a wave. And so there was this debate about whether light was particle-like or wave-like. Now, Maxwell determined that light was an electromagnetic wave. Here's a picture of how it was conceived. If we put labels on this, this might be the z-axis, this might be the x-axis, and the y-axis. The electric field oscillates in the YZ plane. Electric fields are designated with an E, and the magnetic field oscillates in the XY plane. So it turns out that the oscillation of the magnetic field is perpendicular to the oscillation of the electric field. Light in a vacuum traveled at a constant speed c, which is about 3 times 10 to the 10th centimeters per second. His theory differed from Newton's and Coulomb's theory because his theory was a field theory. And what does that mean? Well, if two objects here are exerting a force on each other, we'll call this Q1 and Q2, and they're separated by a distance r, the force itself was thought to reside in the bodies, whether they were charges or masses. In Maxwell's theory, the forces did not reside in the bodies. The bodies created a field, and it was the field that carried the force. And it was also a local phenomenon rather than action at a distance. You can see, I don't know if you can see these, but these are little points where the field has certain magnitudes, maybe direction. If it has magnitude and direction, it's called a vector field. If it's just magnitude, it's called a scalar field, but that doesn't really matter. So each point in space and time has a magnitude that represents the strength of the field at that point. And that was very different than the action at a distance concept. Now, Maxwell united optics, electricity, and magnetism into one theory, electromagnetism, and these were his 4 laws. And we'll talk a little bit about what each of those laws mean. Maxwell's theory was a field theory, and it differed from an action at a distance theory in this way. So if we have a charge here, this plus charge, it sends out a field around it. We have this something called a Gaussian surface. This vector here, this arrow, indicates how strong the force is on the surface of the sphere. And this was usually called a flux line. If you had these little rectangles and flux lines coming out of them, if you added up all the little areas on the surface, that was the total flux through the surface. If this was a minus charge, if we change this to a negative charge, then this arrow reversed itself. Instead of going out through the surface, it went into the surface towards the charge. And that was Maxwell's first law. And what does it tell us? That there are isolated electric charges in nature. The E in this case represents electric field. This is a density, that it's the amount of flux through these little surfaces here. And then you add it all up, and that gives you the total flux. Now, you'll notice that B represents the magnetic field. Now you'll see that this side is equal to 0. And this is Maxwell's second law. So if we have a magnet here, let's say put a magnet in here. In this sphere, we'll put a plus charge here and a minus charge here. Those two charges together will create a flux through the surface. And what happens is that it would go out through the surface here and come back in like this. because this is a minus charge, it's going in, and because that's plus charge going out. And so if we have a magnet, we might give a +1 to all the flux lines going out and a -1 to all the flux lines coming in through a little surface. And if we were to add all the flux lines up, there would be just as many +1s as -1s. So when we added those up, we would get 0. And what that told us was that there are no magnetic monopoles in nature. If you cut the magnet in half, you're going to get another magnet. You don't get two charges. You never get an isolated magnetic charge. If you hear a physicist talk about magnetic monopoles, that's what they're talking about, is an isolated magnetic charge, and there are none. These two equations here tell us the relationship between the electric field and the magnetic field. This one tells us that a moving magnetic field creates, say, an electric field. In other words, it creates a current. So that's illustrated over here. So if we have a magnet and a conductor, a copper wire or something that can conduct electricity, if this magnet moves relative to the conductor with, say, a velocity v not equal to 0, then that will produce an electric current in the wire. On the other hand, if we reverse the poles of the magnet, and this is a velocity v, constant velocity, again it would produce a current in the wire. The current would just move around the other direction. But if the magnet didn't move, if V was equal to 0, no current was produced. This was Maxwell's fourth law, and it said that a moving electric field produces a magnetic field. And usually we call that a current. That J right there indicates a current. This term here deals with special cases, but basically what this says, this is sometimes referred to as Ampere's law. A current, or a moving electric charge, produces a magnetic field. So if we have a current in the wire here, if we create a current, forget the magnet for a minute, and just hook a battery up to it, and we create a current in this wire, then around the current will be created an magnetic field. And those were the four laws of electromagnetism. This law was a problem. This is Faraday's law of induction. So why is it a problem? Well, suppose that we sit Bob 1 on the magnet and Bob 2 on the wire, and if Bob 1 was moving relative to Bob 2, Bob 2 would get a shock. He would know immediately that Bob 1 was moving relative to him. But if we put Bob 1 on the magnet here and he doesn't move, and there's no relative velocity, and we put Bob 2 sitting on the conductor, he wouldn't get a shock because there would be no current. Now, why was that a problem? Well, it was a problem because Galilean relativity was violated. You could conduct an experiment where you would be able to tell the difference between a moving conductor and one that wasn't moving relative to a magnetic field. And Galilean relativity was at the heart of Newtonian mechanics. Someone had to do something about how to reconcile Newtonian mechanics with Maxwell's theory, because they contradicted here. And of course, that's exactly what Einstein did. So how did Einstein fix that? Suppose we have twins here, Bob 1 and Bob 2, and we're going to send a light signal down this way. And exactly the same time as this light signal gets sent, Bob 2 is going to move the constant velocity in this direction. So the light signal would reach Bob 2's position right here. Bob 1, he's going to stay stationary. The light signal reaches his position right here. Now, according to Galilean relativity, these two times are the same. T is equal to T prime. And if that wasn't the case, then I would be able to tell if someone was moving relative to me if I was at rest, and vice versa. Now we can write x prime, this distance here, we can say it's C prime times T prime. T prime is the time on Bob 2's clock, and C prime is the speed of light measured by Bob 2. And we can write x here, this distance here, as C times t, t being the time on Bob 1's clock, and c being the speed of light measured by Bob 1. And so since this distance is the same as this distance, we can write that x is equal to this plus this, which is just c prime t prime plus v times t. But x is just c times t, so we'll substitute c times t in for x, and then carry over this side of the equation. It's the same. And we can bring this vt over the other side of the equation, and this is what we get, and that's equal to that. This is the time on Bob 1's clock, and this is the time on Bob 2's clock. And if t is equal to t prime, which is what Galilean relativity requires, c minus v has to equal c prime. C prime is the speed of light measured by Bob 2, who's moving. Otherwise, the equations wouldn't be equal. So what Einstein realized was that Maxwell's theory required that c prime be equal to c. And if that was the case, then the only way that this equation could be true is if t was not equal to t prime. And that's what he did to fix the contradiction between Maxwell's theory and Newtonian mechanics. So how did Einstein change Galilean relativity? He added a couple of rules. One was called the principle of relativity. And what it said was that it was impossible to determine whether S, that would be Bob 1, was at rest, and S prime, that would be Bob 2, is moving in the plus x direction, or S prime, Bob 2, is at rest, and S, Bob 1, is moving in the minus x direction. In other words, Bob 1 and Bob 2 can both claim to be at rest while claiming that the other twin that's moving. That's the first modification he made. The second modification was that all observers will measure the speed of light to be c, and if we remember, c is equal to about 3 times 10 to the 10th centimeters per second. And those were the two rule changes. So Einstein came up with a set of equations. Here they are. They're called the Lorentz transformations that calculate the times on the clocks and the positions in space of the twins. If Bob 2 is at rest, we use these equations. If Bob 1 is at rest, we use these equations. If you look at either one of these equations, the position of an event in space-time for Bob 2 happens at, this is Bob 2, happens at x prime and t prime. That's location and time. And the position of the same event relative to Bob 1, this is Bob 1, happen at position x and time t. And what we would notice here, and in both cases, that x prime does not necessarily equal x, and t prime does not necessarily equal t. So Bob 1 and Bob 2 would not agree on the position or the time of an event. What Bob 1 and Bob 2 would agree upon turned out to be this. And this is called the space-time interval. They would agree on this, they wouldn't agree on absolute position and absolute time. It's interesting to note that this particular concept was discovered by Minkowski. Hope I can spell his name right, Minkowski. He came up with this idea. He was Einstein's teacher. Ironically enough, he used to call Einstein the lazy dog because he'd never show up for class. But it was he who understood what Einstein had actually done. What Einstein actually did was unify space with time. We could no longer think of space and time as separate entities. When would Bob 1 and Bob 2 agree on the location and time of an event? And it turns out they would agree when v was equal to 0, when they weren't moving relative to one another. So if this v is 0, this goes out, that's 0, that term would go out, that would be 0, and you would get x equal to x prime, so that they would agree on the location. The same thing here, if this term goes out, that term goes out, and t would be equal to t prime. So if they're not moving, then they would agree, but if they're moving at a constant velocity relative to one another, then you have to use these equations to determine what time it is relative to what time it is on the other clock, depending on which ones you use. Now you might ask the question, well, what does this have to do with these equations here? Let's see. We're going to simplify this a little bit and assume that y prime is equal to y, no motion in the y direction, and z prime is equal to z, no motion in the z direction, just in the x direction. So we can get rid of these terms, they cancel out. Then we can write this as x squared minus c squared t squared, and that would be equal to x prime squared minus c squared t prime squared. One of other simplification we can make, we can assume that Bob 2 is at rest. Since he doesn't move, we can assign him the most convenient location, and that would be x prime equals 0. That's an easy simplification, so we can say that x squared minus t squared, c squared t squared is equal to, this is 0, so we can just write minus c squared t prime squared. We can multiply through by minus 1, and that would give us x squared plus c squared t squared is equal to c squared t prime squared. If you'll remember, we can write that x is equal to vt. Distance equals velocity times time. We can remember that. And then we can write that x squared is equal to v squared t squared. So we can substitute for x squared, we can substitute v squared t squared. So we would have minus v squared t squared plus c squared t squared is equal to c squared t prime squared. If we multiply both sides by 1 over c squared. And so what we get is v squared over c squared t squared plus those cancel, so we get just t squared is equal to t prime squared. We can factor out, we'll do it over here, we can factor out the t squared, so we would get 1 minus v squared over c squared. That would be multiplied by t squared, and that would be equal to t prime squared. We can write that t prime is equal to the square root of 1 minus v squared over c squared. Put the square root down here. T. So now if we look at this equation over here, remember we have set x prime equal to 0, so this becomes 0, and you'll notice that this equation then becomes equal to that equation. They're the same. That's how this relates to these equations. So what have we learned so far? Well, Isaac Newton produced a theory of gravity. It was an action at a distance formulation. Maxwell then combined the theory of light and electricity and magnetism to produce a theory of electromagnetism, but it was a field theory, which is a local theory. It gave the source of the force was not in the bodies, it was in the field. His 4 laws are embodied in these equations. They're field equations. And then Einstein made corrections to Newtonian theory by uniting space with time into space-time. However, it only applied to inertial reference frames. Our reference frames were 2 observers were moving at a constant velocity relative to one another. And so that pretty much sums up what we know so far about classical physics. What were the things left to do? Well, it would be nice if we could produce a field theory of gravity, because the action at a distance formulation didn't comport with a field formulation. And so that was one of the things that was on the list. One of the reasons that we might want to do that is that would make it possible, at least potentially, we could unify electromagnetism with gravity. Now, if you remember, this is where we were trying to get to. We were trying to see how we arrive at the general theory of relativity, which is our theory of gravity, and the standard model. And we were able to go part of the way on this side, but we haven't done anything on this side yet. But in the next video, we'll talk about the quantum side of the ledger, and we'll have to do some completion on this side of the ledger. So be sure to tune in.